Class, my name is Moses Colquitt. Myself and my fellow classmates, Rafael, Matt, and Chris, are here to share with you life cycle assessment of 3D printed buildings. So, we look forward to share with you our findings as we conducted our research on this theory. Thank you so much. Hello, class. Moses again. So, on the next two slides, I will be presenting to you guys what LCA is, what it stands for, and the overall effect that it can have on not only our environment but also 3D printed buildings as well. Started. LCA stands for Life Cycle Assessment, which is a method used to evaluate the environmental impact of a product or process throughout its entire life cycle, from example a raw material to a disposable or even recycling. So, in the context of 3D printed buildings, LCA can provide valuable insights into the environmental performance of this construction technology compared to traditional building methods. So some key aspects that can be used are raw material extraction and production, the overall 3D printing process, also transportation and logistics, construction and installation, building operation and maintenance, and then ultimately the end of life and recycling process as well.
Rafael, major differences between conventional and 3D printed buildings from a sustainability LCA standpoint. LCA. From a sustainability and life cycle assessment standpoint, conventional and 3D printed buildings have several key differences. Resource efficiency. Conventional buildings often require extensive use of materials such as concrete, steel, and wood, which may have significant environmental impacts due to extraction, manufacturing, and transportation processes. 3D printed buildings typically use additive manufacturing techniques, which can potentially reduce material waste by only depositing materials where it is needed, thus improving resource efficiency. Energy consumption. Conventional construction methods often involve energy-intensive processes like mixing and transporting concrete, as well as operating heavy machinery. 3D printing can reduce energy consumption by using digital models to precisely control the deposition of materials, potentially requiring less energy compared to traditional construction methods. Construction time and labor. Conventional construction projects typically require significant time and labor to complete, leading to prolonged environmental impacts from construction activities. 3D printing technology has the potential to significantly reduce construction time and labor requirements by automating the building process, thereby minimizing the duration of on-site activities and their associated environmental impacts. Design flexibility. Conventional construction techniques often have limitations in design flexibility due to the constraints of the traditional building materials and methods. 3D printing allows for more intricate and customizable designs, enabling architects to optimize structures for energy efficiency and material use, potentially leading to more sustainable buildings. Waste generation. Conventional construction projects often generate significant amounts of waste material during construction, contributing to landfill accumulation and environmental pollution. 3D printing has the potential to minimize waste generation by using precise amounts of materials and recycling used materials, thereby reducing the environmental impact associated with construction waste. Transportation emissions. Conventional construction materials are often transported over long distances, leading to greenhouse gas emissions from transportation. 3D printing can potentially reduce transportation emissions by enabling on-site production of building components, thereby minimizing the need for long-distance transportation of materials. Maintenance and renovation. Conventional buildings may require regular maintenance and renovation over their life cycle, which can result in additional resource consumption and environmental impacts. 3D printed buildings may have different maintenance and renovation requirements depending on the materials and techniques used, potentially affecting their long-term sustainability and environmental performance. Major differences summary. Overall, while 3D printed buildings offer promising opportunities to improve sustainability and reduce environmental impacts compared to conventional construction methods, it's essential to conduct comprehensive LCAs to assess the environmental performance of specific projects and identify areas for further improvement. Despite its potential benefits, C3DP faces challenges such as proprietary mixers and machinery limitations. Addressing these barriers is essential for realizing the future potential of C3DP in transforming residential construction processes. LCA study, goal, and scope definition. Quantify environmental benefits. Assess the potential environmental benefits of C3DP, particularly in terms of reducing carbon emissions associated with traditional cement production and construction processes. Evaluate resource efficiency. Examine the material and energy efficiency of C3DP process compared to conventional construction methods, including the use of raw material and energy consumption throughout the building life cycle. Assesses structural integrity and durability. Evaluate the longevity and durability of structures built using C3DP technology, considering the use of steel fibers and other reinforcement methods. Policy and market impact analysis. Analyze the influence of policy, frameworks, and market dynamics on the adoption of C3DP technology, following the sustainability incentives and barriers. Scope of the LCA study. Cradle to grave includes all phases of raw material extraction, including cement and steel fibers, transport construction phase, including printing process, building use phase, and end-of-life disposal or recycling. Comparison with traditional construction, the study will compare the environmental impacts of standard residential building constructed with C3DP technology against a similar building constructed using conventional methods. Functional unit. The functional unit will be defined as 1 square meter of livable residential space over a 50-year lifespan. This unit will allow for comparability between different construction methods. Data quality and sources. Primary data will be collected from the ongoing or recently completed C3DP projects where possible. Secondary data will be sourced from existing literature, including peer-reviewed journals and industry reports. Key data gaps will be identified and noted as limitations. Impact assessment categories. Global warming potential, focusing on CO2 and other greenhouse gas emissions. Energy use, the total energy consumption across the life cycle. material resource use, quantities of critical materials used, including water and any non-renewable resource, waste generation, volume and type of waste produced, including during the construction phase and the demolition phase. Assumptions and limitations. Assumptions about the lifespan of materials, energy used during the use phase, and maintenance requirements will be clearly stated. Limitations might include variability in material quality, changes in technology over time, and regional variations in construction practices and energy sources. Critical review. The study will undergo a critical review by external experts in LCA methodology and construction technologies to ensure credibility and reproducibility of the results. This structured approach will help in thoroughly evaluating the sustainability of C3DP in residential construction, guiding stakeholders in making informed decisions regarding the adoption and optimization of this technology.
Hello, my name is Matthew Sloan, and in this section, we're going to discuss the life cycle stages of 3D printing. Those stages include design and planning, site preparation, printing processes, post-printing, inspection and handover, use and maintenance, and the end of life. The major components of design and planning are software, material selection, structural analysis, permitting, and compliance. When selecting software for a 3D printed project, it is important to consider compatibility between different programs, the scale of the project, and the specific requirements of the 3D printing technology being used. The software should also be compatible with local regulations and standards, which can dictate certain aspects of the design and construction process. Material selection for 3D printed buildings significantly impacts the printing process, durability, and thermal performance. The choice of materials affects construction speed, structural integrity, and energy efficiency. Availability, cost, and environmental impacts vary based on material choices, with some being more sustainable or cost-effective than others. Regulatory compliance is crucial due to safety and quality standards. Recyclability at the end of a building's life cycle is a growing concern for sustainable construction practices. Balancing these factors is crucial for achieving durable, energy efficient, and environmentally friendly 3D printed buildings. Structural analysis for 3D printing of buildings assesses the integrity and safety of designs, ensuring they can withstand loads and stresses, using specialized software to optimize for the unique layer-by-layer construction process. Permitting and compliance ensures legal and safety standards are met, which is crucial for the viability and acceptance of 3D printed buildings. There are three major items to focus on for site preparation: the foundation, the utilities and infrastructure, and the accessibility to the site and for the occupants. Foundations anchor a 3D printed building for adapting to soil, climate, and the design for long-term stability. Utility integration is crucial in 3D buildings for functionality, requiring careful planning for water, power, sewage, and gas systems. The key logistics to site preparation is the accessibility, which allows the installation and setup of printing equipment, the in and out of material deliveries, and any other needs the occupant will have once the building is printed. In 3D printing buildings, meticulous printer setup, precise material handling, stringent quality control, and optimal environmental conditions are critical for successful construction, ensuring structural integrity and durability. Calibration, precise positioning, and a stable platform are crucial for ensuring accurate and consistent printing results. Material handling in 3D printing demands consistent supply, reliable delivery, and proper handling to maintain printing quality and structural integrity. Monitoring the printing process for defects in quality and adjusting parameters as needed to maintain structural integrity are part of the quality control of the printing process. Optimal weather conditions are vital in 3D printing, affecting curing time, material performance, and overall printer performance. Once the design cure strength is met, the installation of non-printed items such as roof structure, windows, and doors can proceed. This also includes finishing the interior and exterior of the building. Once the building meets all the codes and standards to occupy, the building is handed over to the owner with the inclusion of documentation and warranties. The LCA related to occupancy involves evaluating environmental impacts from construction to demolition. For ease of repairs, modular design and interchangeable components are key. Repairs can be carried out efficiently by replacing specific sections, reducing downtime and cost. Balancing sustainability with functionality is vital for long-term maintenance and occupant satisfaction. When the building is no longer needed, it can be deconstructed. The materials used in 3D printing might offer more recycling options than traditional construction materials. The life cycle analysis of the building materials and the building itself include the potential for material reuse or recycling.
The parameters that influence the 3D printed building's sustainability impacts. Parameter. What is it? Parameter is a characteristic of a population. It is described or estimated by a statistic obtained from sample data. A parameter can also be a variable in a statistical model that is studied or used to explain an outcome. A parameter can also be an argument of a function. For the purpose of this presentation, a parameter will be defined as a variable used to explain an outcome or a relationship. Just to recap the scope and goals of an LCA, the objective would be to compare the environmental impact of conventional manufacturing technologies and the additive manufacturing process. In doing this, we would base this off of parameters such as energy consumption, the effects of global warming, and the acidification of water bodies. Energy consumption. This is the total amount of energy that is required for a given process, or in this case, the manufacturing process of our end product. In evaluating the energy consumption, we could look at fossil fuel depletion, which would be the total amount of primary energy that is extracted from the earth in order for this process or product to be manufactured or installed. This can be measured in megajoules, and we would want to compare the end product value for all processes. The effect on global warming. In evaluating the effect on global warming, we will look at the global warming potential. This allows for us to make a comparison of the impact of different greenhouse gases. In particular, it is a measure of how much energy the emissions of 1 ton of gas will absorb over a given period of time relative to the emissions of 1 ton of carbon dioxide. We can also look at the smog formation potential, and this would measure the ground level ozone produced by chemical reactions between volatile organic compounds and nitrogen oxides in sunlight. Acidification of water bodies. In evaluating the acidification of water bodies, we'd want to look at the acidification potential, and this is connected to the acid deposition of contaminants on soil, groundwater, and organisms in an ecosystem. We would look at the sulfur dioxide, nitrous dioxide, as the main acidifying contaminants. We would also want to look at the eutrophication potential, which measures the impacts of high levels of macronutrients, specifically nitrogen and phosphorus. This potential would be defined as the potential to cause over-fertilization of water and soil, which can result in the growth of biomasses. The overabundance of this would lead to more algae growth, which would be the start of a chain reaction in an ecosystem that would eventually decompose and produce large amounts of carbon dioxide. As we can see, there are many parameters we want to evaluate in determining the most effective product in terms of environmental impact. It is important to note that we want to look at the whole process, not just the initial process, because these impacts can change depending on what stage of the cycle you're in. So what could be good for stage one in the short term, over the long term life cycle, could actually be worse of a product.
Now I will be presenting to you the opportunities and challenges regarding LCA of 3D printed buildings. To get us started, we will look at the opportunities first. For LCA of 3D printed buildings, the opportunities that it presents is design flexibility. So with design flexibility, you have more complex and customized buildings for designs. This allows for builders or contractors to have total free reign and truly bring their ideas to life. The second opportunity that it allows is material efficiency. So with material efficiency, you will then see reduced material waste through active manufacturing, and also LCAs can quantify environment benefits of reduced material usage. So overall, this will have a positive impact on our environment, and also you will have less debris and things of material on construction sites as well. To continue on with the opportunities for LCA of 3D printed buildings, the first one is supply chain optimization. So one of the key benefits of 3D printed building is the potential for shorter supply chains and more localized production. 3D printing enables the on-site or regional manufacturing of building components, reducing the need for long-distance transportation of materials and parts. This can lead to fewer intermediaries in supply chain and lower greenhouse gas emissions associated with transportation. Also, it also impacts the use of recycling and reuse. So again, life cycle assessments can be used to assess the benefits of incorporating circle economy principles into design of construction of 3D printings, which can help identify the most impactful areas for implementing circular economy approaches, such as choice of materials, the design of joints and connections, and also the logistics of component recovery and to be reused as well. These insights can allow and guide the development of more sustainable 3D printing technologies and construction practices that align with the basic principles of circular economy. So, just like that, there were opportunities for 3D printed buildings. There are also challenges as well. So, some of the challenges that stand in the way for 3D printed buildings is data availability. So, since it is a relatively new technology, there's not a lot of data research, and also the impact on how it will ultimately impact not only construction but also society as a whole. So there needs to be more research done in that area. Also, modeling complexity. So integrating data across product design, manufacturing, construction, and use of in-life stages, is very robust and can be challenging at times. And also just the the variability in 3D printing technology and materials, like I mentioned, is still new. So they have to just make sure that they are still testing it and understand where it is coming from and what it can ultimately do for us and how it can ultimately impact our future as well. And here are the second challenges that ultimately impact 3D printed building, which are lack of standards, uncertainty in use phase, and the scale up challenges. Like we mentioned, this is a new technology that is now coming, so there is no widely accepted standards or guidelines conducting the use of 3D printed buildings. It's kind of just like a free reign system right now, so that can present a challenge because someone can be designing, anyone can design how they want, what they want, when they want, without any regulated guidelines. Also, with the uncertainty in the use phase, predicting long-term performance and maintenance requires of 3D printed components. So, like I mentioned, this is still a new technology that is being used, so there has not been any studies done in the long term to see how these buildings are holding up and how they are able to withstand as time is moving on. And with it being a scale up challenge, people really aren't using this, so it is hard to scale up to see what ultimately it will look like in the future. So those are the opportunities and challenges that I presented you guys with. Thank you once again.
Conclusion. Despite the abundance of technology in various industries, the construction field, particularly in residential home construction, has seen minimal advancements. The growth in construction technology, especially in the realm of additive manufacturing, such as construction 3D printing, has introduced what may be considered old techniques as new innovations in home manufacturing. While 3D printing of concrete structures presents a novel approach to building homes, it also brings forth potential cost savings and reductions in greenhouse gas emissions and material usage. However, despite its potential benefits, C3DP has its drawbacks, including proprietary cementitious mixtures and machinery that hinders progress in the emerging sector of home manufacturing. References.